Okay. Let's see how many people are here. 13. Okay, we'll make do. All right. So, getting into today's section. Okay. Last time we were looking at systems of linear equations where the right-hand side was all zeros, and when does that system have a non-trivial solution? So the concept for today, linear independence, builds directly off of that. Now, so one thing I want to point out is to sort of a recap of what happened last time to set up what I'm talking about today is the following. So let's suppose we have a matrix A that has certain vectors as columns. I'll call those A1, A2, A-N. So those are columns of A. And suppose, like we were talking about last time, this system, AX equals 0, actually has a non-trivial solution, X. So then, what does that tell us? Because when you're describing what this expression, A times X, is, it's a linear combination of these columns of A, and the coefficients of a linear combination are the elements of X. So another way of saying the same thing, X equals 0, is this, x1 A1 plus x2 A2, and so forth. Will give you a 0 vector, and at least one of these coefficients have to be non-zero. If they were all 0, that would be the trivial solution again. So what I'm going to do here is let's assume, since at least one of these has to be non-zero, I'm going to pick one. Let's suppose that x1, that coefficient, is non-zero. So then what I can do is I can solve this equation for A1. So that would be equal to so I can take all the other terms, move them to the other side. So let's go ahead and copy that. Okay. I'm moving it to your side, so I have to negate it. And then I'm going to divide by x1, which is why I had to assume that it was non-zero. So what does this mean in general? So if this system, AX equals 0, has a non-trivial solution, then it is possible to express some column of A. So any column for which its coefficient is non-zero in this non-trivial solution as a linear combination of the other columns. So that means that this column that can be expressed, like A1 in this case, you can think of it as being redundant. So since it's already expressible as a linear combination of these columns, so it's not needed just to describe the span. Why does it do that? The span of the columns of A. So another way of saying this is, at least from this example, we say that A1 is linearly dependent on the other columns. So if I want to describe all possible linear combinations of the columns of A, I don't need to include this one. I can focus on the rest of them. So just because it's already, the dependence is already there. Whereas if this was not possible, if there was no such non-trivial combination, then we could say these columns all have some notion of independence from one another. They all are needed to describe all possible linear combinations. All right. So this is what motivates the concept of linear independence. That's what I'm going to focus on in these problems here. So here we have three vectors, and it's asking determine if they are linearly independent. So now I can give a formal definition. Okay. So whatever set of vectors you have is linearly independent if the only way that this can happen is if all the coefficients are 0. So if the coefficients x1, x2 up to xn are 0, you will get 0. Linear independence means that it's the only way to get 0. All right. So if I have all of those columns put in a matrix, like I did earlier, then if this system has only the trivial solution, then the columns are linearly independent. So that gives us a way to tell if a given set of vectors is linearly independent. We can put them in a matrix like this, and then we can perform row operations on it. We can row reduce it and find out which are the basic variables or pivot variables and which ones are the free variables. So if there are no free variables, then there's only the trivial solution, which is what we saw last time. So another way of saying it is, if there's a pivot position in every column, then the columns are linearly independent. So to illustrate that on these vectors, so I go ahead and put these vectors in a matrix, one vector for each column. So then we carry out row operations. Now, fortunately, there are no row operations needed to eliminate these entries in the first column. We move on to the second column. And here we have a ratio of -4. But actually, what I'm going to do first, I'm going to scale these rows just because the numbers are already pretty nice. I want to make them even nicer since we have integers here. So I'm going to scale both of these rows so that the leading element is equal to 1. So I divide this row by 4, this row by -16. So then we have this, and we can see that these rows, these last two rows, they're not parallel to one another. Neither one is a scalar multiple of the other one. So when we carry out this next row operation, we just subtract the rows. We are going to get something non-zero down here. Okay. So what we have here is the matrix is row reduced. It's now in echelon form. So we look at the columns, look for pivot position. So here we have 1, 1 entry, 5, a 2, 2 entry, which is 1, and then a 3, 3 entry, -1. These three are the pivot positions. Okay. So every column has a pivot position in it. So that tells us the three given vectors that were the columns of the original matrix, those are linearly independent. And we would also see if we were solving system AX equals 0, that system would only have the trivial solution. Okay. Now, if you have problems, if we take a look at the other problems that are in this set, they're all asking for the same thing to determine whether they're linearly independent, or most of these are. But in some cases, it's not necessary to perform row operations, like I just did here. That there can be a faster way to tell if they are linearly independent or not. And in fact, this next problem is an example of that. So sometimes you can determine what this says in the homework by inspection that certain vectors are or are not linearly independent. So this one right here, we see that the second vector v2 is just minus the first one. So when we have a relationship like this, one vector, if you only have two vectors and one is a scalar multiple of the other, then so you can write a relationship like this. Well, you can always rearrange this to put everything on one side and have 0 on the right-hand side, and we have this. So I add up these vectors, and that's 0. So that is a non-trivial linear combination of these vectors that gives you the 0 vector. And that's what I'm pointing out here. We have a non-trivial linear combination with both the coefficients are equal to 1. So they're linearly dependent or not linearly independent. So don't just jump in and say, okay, we got to perform row operations. Not necessarily. Sometimes you can tell really quick, like this one, like in this case. All right. I'm going to make up another example, kind of like this one. But I want to add another dimension to it, literally and figuratively. Okay. All right, so here we have this first vector v1. Okay, and then I want two more vectors. All right, so for v2, I'm just going to negate these. All right, and then I'll put something else. Okay, for v3. All right. Now, using the same reasoning as in the original problem, so vectors v1 and v2 because of scalar multiples of each other, those are linearly dependent. So if we look at the whole set of vectors, v1, v2, v3. Is linearly independent. So all it takes is one vector. If you have a subset that's linearly independent, it spoils it from a whole thing. So that makes a whole set linearly dependent. However, if I ignore v2, for instance, I just focus on v1 and v3. So anytime you have just two vectors, you just check if one is a multiple of the other. Is it possible to multiply this vector by some number, scaling it, to get this one? Well, it's definitely not possible, because if I take this vector and multiply it by any number, third component's always going to be 0, whereas it's not here. So this set of vectors, v1 and v3, or if I'd chosen v2 and v3, that one is linearly independent. So what you can say is either one of these vectors is redundant. So you toss out one of them, and then you have a from this set of 3, and then you have a linearly independent set. All right. Now, unfortunately, in this case, it's not so easy to tell if this one's linearly independent or not. But it's a good opportunity to show certain things you can do with row operations to try to make it easier to determine if we have linearly independent columns, or just dealing with this matrix to solve a system. Because normally what you do is you would find a multiple of this row, of the first row, to eliminate entries below it. But here it's 0, so it's not possible. So what you would need to do is interchange some rows so that you can use this element up here to eliminate ones below it. Now, technically, you can pick any of these rows to move up here. I'm going to choose the one with a 1. 1 is a nice element to work with as to eliminate other elements. So my first row operation is to swap the first and last rows. So we have this. So now I can just so to find the correct multiple of this row to subtract from the others, I just look at these elements that I'm trying to eliminate. So for instance, I can take 3 times row 1 and subtract it from row 2, and then I can add rows 1 and 3 together and get rid of those elements. So sometimes it's helpful to, especially when you have matrices like these that are all integers, maybe able to scale a row or swap rows to make subsequent row operations easier. The same applies for these rows that are remaining. Here we have all of these entries are multiples of 8, and same thing down here. This row, because it has a 0 in this position, we might as well move it to the last. So swapping the last 2 rows. Because then it gives work on these to figure out everything else. What we can already tell, though, is this row is certainly not parallel to any of the other ones. These rows are not parallel either. So if I go ahead and scale them for convenience, everything here is a multiple of 8, so I can divide the second row here by 8, and the third row by -8, just to get everything in lowest terms. So we can see that when these rows are not parallel. So if I for row operations on them, I'm not going to get a row of zeros. But again, I like to work with a 1 for eliminating. So if this is not convenient, So I'm going to swap again. And move this one up here. So then I could take twice this row to eliminate this element. And this is what we get here. Now, you could go further to get a proper echelon form. That would involve taking a multiple of the third row to subtract from the last row, and you get a row of zeros down here. But as far as addressing the original question, do the columns of this matrix form a linearly independent set? We can actually stop here because we can see that every single column has a pivot position in it. So this one, and this -3 here. So it's safe to conclude that there's a pivot position in every column. So these columns are linearly dependent. Now, if I was to have a problem like this on the test, and certainly there will be, at least a problem where you're given some vectors and you're asked to determine if they're linearly independent or not. I would do my best based on the selection of problems that are there, not to include a problem where, okay, you go ahead and do this, and then it asks for a reduced echelon form, because we definitely do not need the reduced echelon form to determine if these columns are linearly independent. I mean, I want to keep a focus on like the question that's actually being posed. And if literally all of those questions had an option, I would just tell you guys not to do it. After today, we have 2 sections of chapter 1 left to cover. Then you'll have seen all the material that's going to go on test 1. Then I'll be able to tell you more about it. Okay. Now, this one seems like it might be quite a bit of work to determine if these columns are linearly independent. But in fact, it's literally no work at all, because we can actually conclude immediately that these columns are not linearly independent, because we only have 3 rows. Now, to be linearly independent, every column, all 4 columns, have to have a pivot position. But every row can have, at the very most, 1 pivot position. So anytime you have more columns than rows, you can't have a pivot position in every column. So if you have more columns than rows like this, so a shorter but wider matrix, then you can conclude immediately the columns are not linearly independent. Now, if you want to confirm by getting a reduced echelon form, for instance, because some homework problems do require that. So at least here we conveniently have a 1, so we can use twice this row to eliminate the 2s in the other rows. Okay. So same thing. Okay. Now these 2 rows are not parallel to one another. Like if I take this row, multiply it by 3, I'm going to get 3, 6, and -6, as opposed to 8 and -8. So there will be 3 pivot positions. There will be a pivot position in every row. but this is as far as we get for a plain old echelon form. And so columns 1 through 3 have a pivot position. The fourth column absolutely cannot. Now, if we want to go all the way to reduced echelon form, okay, just for convenience, we all the pivot positions have to have an entry of 1 for reduced echelon form. So I'm just going to divide by 2. And then I can use this row to eliminate these entries here. So I can take twice this row to get rid of that one, and I can take -3 times it to get this one. Okay, and what does that give us? Okay, so those entries are eliminated, and then the same thing to deal with the first row. Okay, so now this is this column has a pivot position. It's the only non-zero entry in this row. And then we need to, similarly, this needs to be the only non-zero entry in its row. So we have to use this row, the second one, to get rid of this 2 here. So that's the last row operation needed to bring us to reduced echelon form. Now, so here we have pivot positions, although we knew where we were already just by getting to echelon form. The only reason I'm working this out is that for this problem, that MyLabs requires computing to reduced echelon form. Now, but also about this problem, the question asks for reduced echelon form of the augmented matrix for the system AX equals 0. So that means there'd be an extra column here of 0. So I did not include that here, but the homework problem would require it. So there's a heads up about that. But yeah, there's definitely I guess a philosophical difference between myself and I guess the textbook and therefore MyLabs as to the importance of the reduced echelon form in the whole scheme of things. But it's my preference that will matter when it comes to how tests are set up. Okay. Our questions up to this point about determining whether given vectors are linearly independent or not. Now, these next 3 are quickies, where one can tell very right away, again, by inspection, if a vector is linearly independent or not. So for these problems, there's no need to perform, to slap them in a matrix and perform row operations. Like for this one, there's simply too many vectors. Actually, what we have between these 3 problems is almost like a Goldilocks problem. Here you have too many, just the right number, and then not enough. So for linear dependence, having too few vectors is fine, but having too many vectors is not. There's no way that if you have vectors with m elements, and if the number of vectors is n greater than m, you're not going to have linear independence. So that settles it right there. Okay, so just so a general statement that I can make. Okay, so if you have too few entries per vector relative to the number of vectors that you have, they will be linearly dependent. Now here we have vectors of length 3, and you have 3 of them, so that's not this doesn't apply. One of them is a 0 vector, so you can certainly have a non-trivial linear combination of these being 0 just by picking this one. So if a set of vectors want to be linearly independent, they all must be non-zero. So toss out any any 0 vectors that you have. And then here, okay, vectors of length 3, we only have 2 of them. Okay. Now, when you have 2 vectors, you want to check, is one of them a scalar multiple of the other? That almost happened here. Like each of these entries is equal to these divided by plus or minus 3, but that's just it. It's plus or minus. So if this had been a minus right here, a -1, then this vector would be equal to -3 times this. But since that the ratios are not all the same, these vectors are they're not, so since they're not scalar multiples of each other, they're linearly independent. So that's a quick way to check when you only have 2 of them. If you have more than 2 vectors, but you spot that 2 of them are multiples of each other, again, the question is answered right away, that the set as a whole is linearly dependent. Okay. So now for this last one, so it's something that would not be obvious just by looking, but you can almost tell from the first elements here. If I take this column, first column, and then I multiply the second column by 2, add them together, then I'm going to get the third column. So I have 4 plus 2 times 2 equals 8, and then here I have -7 plus 2 times 2 gives me -3, and then -3 plus twice this would give me -5. So in general, third column equals first column plus 2 times the second column. So this relationship that is given, you want to write that as a vector equation. So, okay, I'm going to put this on a new page. Okay, so taking an equation that's given in words, we have this. So what the question asks is, what's a non-trivial solution of AX equals 0? And thankfully, without performing row operations. So what I can do is just rearrange this and get a 0 on the right-hand side by itself. Okay. All right. So by rearranging this, I get 0. But then what I want to do is I want to express this vector equation and as a matrix equation. So writing it this way, A1 plus 2A2 minus A3 is the same as writing it this way. We have a matrix A1, A2, A3 times this vector. So the coefficients of a linear combination, 1, 2, -1, go in this vector right here. So here we have matrix times vector equals 0. So that vector is a non-trivial solution. So what you do is, from whatever relationship that's given here, you write it this way as a vector equation, and then just rearrange to have 0 on the right side. Whatever coefficients of your vectors are, that's your non-trivial solution. So in general, like when you need to find out if certain vectors are linearly independent, see if you can determine it by inspection. There are certain criteria that you can apply quickly, like do you have too many vectors? Is there a zero vector? Is one vector clearly a multiple of another? Those things you can use to try to get an answer quickly. If none of those apply, then the thing to do is perform row operations. You put them in a matrix and row reduce it. Echelon form is enough to answer the question of linear independence. See if you can find a pivot position in every column. Okay. And if so, then they're linearly independent. All right. So what does this say about we talk about system X equals 0. So what does linear independence tell us? It at least rules out certain things. Okay. All right. So if the columns of A are linearly independent, we already know in that case AX equals 0 has only the trivial solution. So in that case, either AX equals B has a unique solution, or no solution at all. So if you have a possibility of infinitely many solutions, is precluded by the columns of A being linearly independent. So which one it is just depends on the choice of B. So either B is a linear combination of the columns of A, or it's not. So therefore, it's a unique solution or no solution. And we can also say if they are linearly dependent, then if there is any solution, there are infinitely many. So in other words, in this case, when the linearly dependent columns, the unique solution is taken off the table. There still might be no solution, but there's also a possibility of infinitely many solutions. And the reason why is because you actually have non-trivial solutions of AX equals 0. Okay. Okay. All right. Does anyone have any questions either about what's been covered here or about problems you are currently working on in my labs? And be sure to unmute yourself if you do. So one thing to keep in mind as we get closer, it's still, yeah, it's only September 2nd, so it's a little less than 3 weeks before it's time to window opening for the taking a first test. As I mentioned earlier, I'm going to put a practice test out, and at that time, I'll be able to tell you what the parameters are for administering the test. Like, you'll see how many problems there are, how much time, etc. And what I would suggest is I'm going to set up a practice test so that you can you can try it multiple times. So maybe take your time going through it the first time, and if you can, after you've done that, and you got a feel for what it's like, try again, but with whatever time limit I've set. Actually enforce that for yourself, so that you can work on solving these problems efficiently, and get your rhythm down, because you're basically going to be going through similar motions, just with different numbers and that sort of thing, when it's time for the real thing. So to keep in mind to try to carve out that amount of time for yourself when the practice test is put out there. I'm not going to make it some marathon, because our class time is an hour and 15 minutes, and so what I'm going for a time frame is something along those lines. But I also my lab's actually, I believe, and I'll check on this because I know I've done it in the past with classes I've used my labs for, where they actually have data gathered from all the students using these problems nationwide, like how long do certain problems take, and that's something that I can take into account. And like if I see a problem here that on average is taking students 30 minutes, then I don't think I want to include that one. So okay, so that's all I have to say about the test at this time. As I said, more info will be forthcoming as I get through these last sections. So we're off for Monday, Labor Day. So our next class will be in a week. So I'll have 1.8 being covered next Wednesday. Then there'll be 1.9 after that. The following Monday, which is the 14th, and then that Wednesday will be so 2 weeks from today. That'll be a review. At that time, a practice test will have been made, so that I'll be able to talk more fully about it then. So that's what that class will be for. Okay. All right. So what I'll do is I will end the recording at this point, but anyone's welcome to stick around and ask questions.